Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to provide examples or demonstrate how to cut systems apart and draw free body diagrams of various parts of the system and how Newton's second law applies to the system as a whole and individual pieces of it. So what we're looking at here is just this nice simple example I made up with these three objects that are connected by cords, ropes of some sorts, here and here. And then somebody somehow is pulling on the system with a 500 Newton force to the right. Now for this example, again, I want to keep this simple. We're going to assume frictional coefficients of 0. So I'll say our friction approximately 0, or frictional coefficients of approximately 0. We're not going to worry about that for this example. So it's all about Newton's second law. So when we think about Newton's second law, it's this. Newton's second law is F equals ma. Now it's very important to know, what do we mean by F? In Newton's second law, the F is what's called the net force. All right, that's very crucial to understand. It's the vector sum of all forces acting. And Newton's second law applies to the entire system, but it also applies to pieces within the system. And it doesn't have to be just the individual pieces. It can be, you can cut them apart like so. Right? Now, I'm going to take some time here and really talk about, how you define systems and what the equations look like. So in this example, I would typically recommend people start by defining their system like this. And the reason is this. Inside of that system, there's a pair of ropes here, right? There's one right here and another one right here. And these ropes, they create forces that we call tensions. And the tension in this rope right here acts to the right on this object, right at that location, and it acts to the left on this one. Now, those forces, as far as that system is concerned, add to 0. They're equal forces in opposite direction. That's an example of an internal force. So by defining our system the way we do, all of it together, we don't need to worry about what's happening here because that force is internal to the system. Same thing goes with this rope. This force here, also internal to the system. So by defining our system as the whole thing, that allows us to basically ignore these because those become internal forces and don't need to be considered. See, it might seem a little weird, like, can we really just ignore that? And the answer is yes. See, as far as this 500 Newton force is concerned, these things can be glued together, or this can be one big rigid object, and the 500 Newton force wouldn't know the difference. Those internal forces are not affecting the acceleration of the overall system. So now if we complete our free body, we have to add external forces. Now, I'm going to get this out of the way here. Usually, I always recommend people, save their big picture here for describing the entire problem and not try to make free body diagrams out of it. I'm going to go ahead and just use this one picture for my free body of the entire system, and then we'll talk about what it looks like when we cut the system apart. So let's talk gravitational forces. Oops. So there are definitely gravitational forces acting on the system. You have choices on how you can handle that. You could either draw let me get color a little easier to see. We could either draw 3 separate force vectors, each one with its own mg. We might call it something like m sub a, g, m sub e, g, and so forth. Or we can do this. And I'm going to go ahead and just do this here. I'm going to draw one single force vector. For now, I'm just going to put it roughly in the center of the system. Where it's applied is not super important for this example. And then that force vector, I'm going to call it mg here. In this example, using a single force vector, we would use 100 kilograms. Now, surfaces in contact. There's surfaces in contact here here, and here. So there are 3 different normals in this problem that are vertical. We could either draw 3 separate normals and give them names, or what I'm going to do instead is just like I did with the gravitational forces, I'm just going to group those together into one force, one vertical force, and call it a normal force. Now, when you're drawing free bodies, normally you also, what's the word I want here, try to make your forces proportionally correct. Now here's what I mean by that. In our picture, this 500 Newton force is drawn to this length. The weight, the mg for this system is about 1,000 newtons. I'm getting that from 50 plus 20 plus 30, that's 100 kilograms times g, which is about 10. So this vector right here should be about twice as long as this one. I mean, technically it should be exactly twice as long. I've got it slightly longer. I'm going to call that good enough and move on. All right, so now that's it for the free body. If there were frictional forces, we would include them, but we're not in this example. So that's it. When you apply Newton's second law now, right, here's what that looks like. 1, the sum of all forces is equal to 0 in the y direction. Now, how do I know this? There's no way this thing's going to accelerate up. It just isn't. The circumstances don't dictate it. There's no doubt this thing's going to accelerate to the right. And that means that equation-wise, n minus mg equals 0. The next equation we can write for the free body is the sum of all forces, I'm going to call this the x direction, equals ma. Because this thing is going to accelerate to the right. And when we look at our free body, this is the only force in that direction. So 500 newtons equals m, which is 100 kilograms, times a, the acceleration of the system. So this system is going to have an acceleration of about 5 meters per second by the time we solve that for the acceleration. Unit-wise, by the way, a newton is a kilogram meter over second squared, so it's going to work out to meter per second. So there's an example of drawing a free body of a relatively simple system and applying Newton's second law. Now I'm going to go back. Hopefully I can go back quite a bit more here. Oops. Oh, that's all it's going to let me do. All right. Now what I'm going to do is cut the system apart and draw free bodies of different pieces. So imagine that we wanted to know maybe the tension in this rope. So in order to do that, what we need to do is draw a free body that has that tension in it. So there's a few possible free bodies to draw. We could draw a free body of this part of the system, or a free body of this part of the system. Either one will work. I'm going to go ahead and just draw a free body of this part of the system. Now, when you draw a free body, usually what you want to do is this. You want a picture of the object. Oops. By itself. There's my toolbar here, some things I want to get rid of. Using a new program here, so got to kind of bear with me here a little bit. Oh, there we go. Don't really need this anymore. Okay, good enough. Now I'm going to start putting force vectors in now. So this object has a weight, down, equal to mg. This m is 50 kilograms. Okay. Surface and contact right here. There's a vertical normal on this object. Now, it's not the same as this normal. It really can't be listed the same either. I can't call it the same thing. I'm going to do this. Let's call it N1. Calling this box 1 and 2 and 3. And again, here's something else in contact. That box is being pulled to the right with some sort of force here. Now, this is the type of force that we call a tension. So I might call it something like tension 1. Right, so now this rope here, I'm calling that rope 1. And throwing friction out, that's it. That's the only thing that's acting on that 50 kilogram mass. Now I'm not going to worry about the horizontal direction or the vertical direction. I'm only going to worry about the acceleration direction. That object is accelerating to the right at a value that I found previously in the video here of 5 meters per second per second. So when we write our Newton's second law equation for the free body, sum of all forces equals mass times acceleration. My standard rule of thumb, if you know the acceleration direction, call that positive. And the only force in the x direction is this one. So we get T1 equals ma. And we have values here. I'm going to go ahead and put those values in. The mass is 50 kilograms. And we already know that the acceleration of the system was 5 meters per second, and we get a number for tension 1, 250 newtons. By the time we multiply that out, a kilogram meter per second squared is what a newton is. So the tension here is now known in this rope. That tension acts to the right on this mass at that location, and it acts to the left on this one, on the 20 kilogram mass at that location. And that's an example of Newton's third law. Remember, forces always appear in pairs. All right, next we're going to talk about finding this object, or the tension in rope 2 there. There's several, lots of different ways to do that. We could draw a free body of this part of the system. That would work because it would have this external tension. We could draw a free body of this. Now, if we draw that free body, tension 1 is now an internal force. Tension 2 will show up. Or we can draw a free body of this part of the system. Here, both tensions will show up, but the 500 Newton force will not. And I think we'll do that one. So what I'm going to do is I'm going to take this thing. I'm going to copy it. A lot easier to do with my computer system than maybe at home working on paper, but I'm going to go ahead and get this stuff kind of out of the way. All right, and we'll start putting force vectors in this one. So this object has a certain weight. Now, although I think I kind of skipped it, you'll notice I drew this vector quite a bit smaller. That object has a weight of 500 newtons, so technically speaking, it should have been drawn to that length, but no harm, no foul. This one is about 200 newtons in weight, so I draw it a little bit, I put that mg a little smaller. That's mass 3 times g. In this case, mass 2 times g. In this case, that weight is about 200 newtons. Again, surface in contact here, that's going to give us a vertical force on this object. Normal, let's call it normal 2, the normal acting on 2. Now, this 250 Newton force we found, remember, that was coming from this rope right here. That force acts to the left, to the right on the green mass, on mass 1, but it acts to the left on mass 2. That's Newton's third law. Now, whether we call that tension 1 or 250 newtons, doesn't really matter. I'm going to go ahead and just call it 250 newtons. And right here, we have a rope pulling mass 2 to the right. That's going to create another tension. Now, I don't know a value yet. All right, I'm going to call it tension 2, but I do know it has to be larger than this one because mass 2 is accelerating to the right. And there's our complete free body for the middle mass there. Then we can write a Newton's second law equation for it. Sum of all forces equals mass times acceleration. Might as well do right positive because that's the way this thing's accelerating. Tension 2 is to the right, minus the 250 newtons is to the left, equals m. That's the mass of the system. That's 20 kilograms times a, the acceleration of 5 meters per second squared. Sorry for going off the screen there on you. And that can be solved for tension 2, no problem. That's going to be, what is this, 100 plus 250, 350 newtons, acting on mass 2. So, important things here. You can draw free bodies of entire systems, like I did at first, circled in green, or you can cut the system apart and draw free bodies of the individual pieces of the system. And Newton's second law applies to each one of these free bodies. So I hope that this video helps out, gives you ideas how to apply Newton's second law and cut systems apart and look at free bodies of the different parts of the system. Have a great day.